This video is for lesson 15-5 about the inverse of a matrix. Recall that two real numbers whose product is 1 are called multiplicative inverses. We also call those reciprocals when we're talking about real numbers. For example, the number 2 and the number 1/2 are multiplicative inverses because when you multiply them together, the answer is 1. Also recall that every real number except 0 has an inverse. A 2 by 2 matrix can also have an inverse, but only if its determinant is not 0. Here is the definition of what an inverse matrix is. First of all, here's the symbols that we'll use to mean inverse matrix. When you see a capital letter, when we're working with matrices, and in the upper corner when you see a -1, that means the inverse of matrix A, or you might call it A inverse. This -1 in the upper corner is the same symbol we used for inverse functions in an earlier section. Back in that earlier section, we would have like f with a little -1, and that meant the inverse of function f. A matrix is the inverse of matrix A if, when you multiply them together, you get the identity matrix. Remember, the identity matrix is a matrix that has 1s and 0s in it. For example, the 2 by 2 identity matrix is 1, 0, 0, 1, where along this main diagonal from the top left corner to the bottom right corner are the 1s, and the other two numbers are 0s. So for two matrices to be called inverses of each other, when you multiply them together, it must create this answer matrix. And this has to be true no matter which matrix you write down first. So writing this matrix first and timesing by this one has to make the identity, and writing this matrix first and timesing by this one has to make the identity. Here's an example problem. Using multiplication, let's verify that this matrix and this matrix are inverses. Let's multiply them together, but we have to do this in both orders. So 2, 3, 1, 2 times, and now over here, 2, -3, and -1, 2 makes, and let's see what answer we make. We want to know if it makes the identity 1, 0, 0, 1. So let's run through the multiplication process. 2 times 2 is 4, plus 3 times -1, which is -3, and that makes 1. Now we'll do this top position. 2 times -3 is -6, plus 3 times 2, which is 6, and that does make 0. Now let's do the bottom left position. 1 times 2 is 2, plus 2 times -1, and that does make 0. And now we'll do the bottom right position. 1 times -3 is -3, plus the 2 times 2, which is 4, and that does make 1. So this does make the identity matrix, but even that's not enough to know for sure that these are inverses, not until you multiply them in the other direction as well. So let's rewrite it, and this time put the 2 and the -3, and the -1 and the 2 as our first matrix. And then we'll write the 2, 3, 1, 2. When we multiply together, we're wondering, do we get the 2 by 2 identity matrix? Let's run through the multiplication process. 2 times 2 makes 4, plus -3 times 1, which is -3, and that does make 1. Now let's do this top right number. 2 times 3 is 6, plus -3 times 2, which is -6, and that does make 0. Now we'll do this bottom corner by using the second row and the first column, and that does make 0. And finally, we'll do this last number by using the second row and the second column, and it does make 1. So because we get the identity matrix both times, that is our verification that these two matrices are inverses. Now in the textbook on page 563, it works out the technique for how you discover the inverse matrix. In the example we were just working with, we were already given two matrices and we wondered if they were inverses. What if you're not given a matrix that you think is the inverse? Then you've got to find it yourself, right? So this is the technique that you use to find it. It's this math formula. To find A inverse, notice what you're doing. First of all, you're using the determinant of matrix A. So in an earlier section, we talked about how to find the determinant of a 2 by 2 matrix. The other thing you're doing is you're doing some multiplication of this number out here times a matrix. That was scalar multiplication from an earlier section, where you multiply the number in front of the bracket by each of the entries inside the bracket. And notice as well that in here, we're rearranging the positions of the different things. Because if our original matrix has the A, then the B, and the C, and then the D, notice how this changes that up somewhat. Let's do an example problem. Find the inverse of matrix B if this is matrix B. Let's run right through the formula. First of all, we're going to go 1 over the determinant of matrix B. So let's find the determinant over here on the side. Remember, for determinant, you can use the delta symbol, or you can put bars around the B. It means the same thing. Multiply diagonally from top down to the bottom right. 2 times 5, that's 10. Then subtract the other diagonal, -1 times 4, which is -4. This determinant is 14. So right here in the bottom, fill in 14. Now we're going to multiply by a 2 by 2 matrix. And the formula tells us how to get the numbers in the different entry positions. Originally, the A is up here and the D is here. Now look in the formula, it says D and A. How would you describe in words what you're doing with those two numbers? You're switching their positions. So in our problem, if this is 2 and this is 5, we're going to put the 5 here and the 2 here. Now in the original matrix, here's where B is, here's where C is. Now in the inverse, look what this says, -B, -C. How would you describe in words what that's showing us? We're not switching positions, but we're changing the signs. So if this number is 4, then this is -4. And if this number was -1, then this is now +1. To get the final answer, multiply that 1 over 14 to all 4 of those numbers. So we have 5/14, then -4/14, which does reduce to -2/7. Down here it's 1/14, and then over here it's 2/14, which does reduce to 1/7. So here in the brackets is the inverse of matrix B. It's called B inverse. Let's do another example. Let's find A inverse if this is matrix A. And we'll follow that same technique. So A inverse equals 1 over the determinant of matrix A. Well, let's just go over here on the side and find that determinant. So multiplying diagonally, -1 times 0, that's 0, then minus, and then this diagonal, 2 times 3. And 0 take away 6 is -6. So our denominator is -6. Now we're going to multiply by a 2 by 2 matrix that we make from our original. What do you do with these two numbers? You switch their positions. What do you do with these two numbers? You change their signs. Now multiply that scalar to those 4 numbers in the brackets. So -1/6 times 0 is still 0. -1/6 times -3 is 3/6, which reduces to a half. Now down here in the corner, -1/6 times -2 is 2/6, and that reduces to a third. And then over here in the bottom corner, -1/6 times -1 is +1/6. So this matrix right here that we figured out is the inverse of our original matrix A. A matrix equation that involves multiplication can be solved using inverses. First, consider how you would solve this regular equation. To get rid of the coefficient of the x, we would multiply by the inverse of 1/2, which is 2, right? So we would go times 2 on the left and times 2 on the right. Those cancel out, just leaving a 1, and we get x equals 10. We can do the same thing with a matrix equation. Here is a matrix equation. It has a matrix, in this case a 2 by 2 matrix, being multiplied to an unknown matrix called matrix A. Remember, in this chapter, any capital letters refer to matrices. And that's equal to some other matrix on the right side. Notice how similar this is to our example up here about real numbers. It has the same general pattern to it. So the technique to solve it is the same. We want to multiply on the left side by the inverse of this matrix. That's how you'd get it to cancel away, and the letter A would be alone. And whatever you multiply by on the left side of the equation will multiply by the same thing on the right side. And that's why I left this blank spot here, so that we could write times and fill in the matrix that we're multiplying by. So we want to multiply by an inverse. We need to know what the inverse of this is. Let's figure that out over here in the margin. Well, it's 1 over the determinant. Well, we got to find the determinant. 1 times 3 is 3, minus 1 times 2, which is 2. So that just makes a 1 in the denominator. And then you multiply by a 2 by 2 matrix that's created from those 4 numbers. What do you do with the 1 and the 3? You switch their positions. What do you do with the 2 and the 1? You change their signs. And when you multiply by 1 over 1 in the front, you're really just getting those same 4 numbers. Okay, we're ready to solve this equation now. On the left side, let's multiply by that inverse matrix that we figured out on the side of our paper. And on the right side, let's multiply by that same matrix. Notice that I'm doing what's called a left multiplication both times. Okay, on the left side, because these are inverses, they will make the identity. And the identity matrix is kind of like just canceling away. So we get the letter A alone. On the right side, when you multiply a 2 by 2 to a 2 by 2, you get a 2 by 2 matrix. Let's figure out those numbers inside there. 3 times 0 is 0, plus -2 times -1, which is 2. So this makes 2. Now we'll do this number. 3 times 1 is 3, plus -2 times 2, which is -4, and this makes -1. Now we'll do down here. -1 times 0 is 0, plus 1 times -1, which is -1, so this is -1. And finally, this last number. -1 times 1 is -1, plus 1 times 2, which is 2, so this makes 1. We have figured out our unknown matrix A. And we did it using a method that's just like you use with real numbers. It's just we're doing this with matrices. Let's do another example of solving an equation using this multiplying by an inverse matrix technique. So we want to get matrix A alone. That means we want to cancel the coefficient matrix that's in front of it. We need to know what the inverse of that matrix is. So let's go over here in the margin and find that inverse. It involves going 1 over the determinant. So 2 times 4 is 8, minus 6 times 1, which is 6. That makes 2. And then multiplying by a 2 by 2 matrix created from these 4 numbers. So you switch the 2 and the 4, and you change the signs on the 1 and the 6. Then when you multiply everything through by 1/2, it makes 2, -1/2, -3, and 1. Okay, what was this thing we were figuring out over on the side? We were finding the inverse of this matrix so that we could multiply by that on the left side and over here on this side. So let's show that now. So we have the 2, -1/2, -3, 1, and we want to times it to the 2, 1, 6, 4, and then the times a. And then over here on this side of the original equation, we want to take that same inverse that we figured out and write it down. And show how we're multiplying it to the 3, 2, 0, 1. These two just cancel away. The letter A is alone. And on the right side, we're actually going to perform this multiplication to see what we get. 2 times 3 is 6, plus -1/2 times 0, so this just makes 6. Now this one here, 2 times 2 is 4, plus -1/2 times 1, so 4 and -1/2 is 3.5. Now down here, -3 times 3 is -9, plus 1 times 0, so that's just -9. In this last spot, -3 times 2 is -6, plus 1 times 1, which is 1, so -6 plus 1 is -5. Here is our answer for matrix A. You'll notice how being able to do those multiplications in your head and keeping track in your head makes it faster to get those 4 numbers figured out. If you've got to actually take the time to write down all the steps to get those numbers, you can do that. It just takes more time, but it might make you more accurate. And you certainly can use a calculator to help avoid arithmetic mistakes. For instance, when you want to define like the 3.5, to get that number, you're using, right, the first row and the second column. So on your calculator, you could type 2 times 2 plus -1/2 times 1, and then push enter. And that way you're going to avoid any arithmetic mistakes. Let's summarize the lesson. We looked at how to solve what's called a matrix equation, how to figure out what an unknown matrix is. And the technique is to first find an inverse matrix and then to multiply by that inverse matrix.